Welcome to my presentation titled Electromagnetic Wave Sensor for Proximity Target Detection under Radio and Radar Coexistence at 2.4 GHz ISM band. Ever since I was little, I've held a high regard and curiosity for radios and wireless communication devices. Likewise, the research project I conducted under mentors from Lockheed Martin reflects my interest in radios and more specifically about the sensing capabilities and object detection frequencies of antennas. My research project will present an overview of an experiment that I conducted where I modeled a wireless sensing system solution consisted of TX and RX antennas, metal objects for sensing, various off-the-shelf hardware components, and a spectrum analyzer. In addition, this presentation will briefly mention some theoretical elements and studies that factored into my research. For the general experiment setup, the sensing system was set up as seen on the slide. Next, I measured the leakage of the transmit signal to the receiving signal and the router strength. It's important to note that the phase shifter adjusts the phase of the radar signal and the amplitude controller adjusts the amplitude of the radar signal so that it is matched with the phase and amplitude of the signal coming via the RX antenna. These matched radar signals are then cancelled out the delta port of a 180-degree hybrid coupler. Lastly, for the final experiment, I set up a metal kitchen tool to approach and pass through the antennas, measuring the distance of the tool and the strength of the signal reflection through the spectrum analyzer. This reflection by the object, which is the metal kitchen tool, essentially breaks the balance state set in step 2 before, and the received power will increase as the metal object, the kitchen tool, approaches the antennas. Through my third experiment, I demonstrate the radar sensing operation, which enables environmental sensing capabilities while also communicating. Here in the image you can see my resources used for the experiment. Firstly, I had the 2.4 GHz radar signal source from my computer, and then below that I had the spectrum analyzer in HP8593A to measure the received signal, DC power supplies for phase shifter and attenuator controls, the TX and RX antennas, and the metal object, which was the kitchen tool. I also had the power divider, phase shifter, the attenuator, which is the amplitude controller, a coupler, a 180-degree hybrid coupler, and the TX-RX antennas as seen below. This conveniently matches up my diagram I outlined during my experiment. For the results, there is some theoretical information I used from my experiment. To calculate the theoretical power received at the RX antenna over a certain distance, I used the equation PR equals PT GT sigma A divided by 4 pi r squared, which simplifies to K over R to the fourth power, which is the fitting parameter in the function of signal power and antenna gain. Through this equation, I found that the strength of the received power at the RX antenna decreases by a factor of the fourth power as the distance increases, as illustrated by the R to the fourth. From this, the graph is a downward sloping exponential graph. However, it is impossible to calculate the exact value of K due to difficulties estimating the radar cross-section of the metal object used in the experiment. Thus, I plotted the theoretical PR when K equals 0.5 times 10 to the 12th, 1 times 10 to the negative 12, 2 times 10 to the negative 12. There's a good correlation between the measured data and the theoretical PR with K equals 1 times 10 to the 12th and 3 to 16.5 centimeters. However, when R is greater than 16.5 centimeters, PR is too small and noisy, as illustrated by the noisy response in the graph to the right. The work in my experiment verified the successful radar sensing operation while receiving the Wi-Fi signal at 2.4 GHz, while also demonstrating radar and radio cooperation at the same frequency signals. The experimental data verifies the theoretical estimations I referenced during my presentation. This technology holds promise in the areas of safety, computer technology, biomedical sensing, and gesture technology, especially in areas like medical implants, crime safety, and robotic gestures. Radar sensing is an emerging new paradigm.